algebra students. Today's lesson is going to be on equivalent equations and rewriting these equations to find equivalent equations. Our objective for this lesson is going to be let's investigate what makes two equations equivalent. At this point, I've said the word equivalent twice now, so you might be remembering what equivalent means. To help us explain the idea of something being equivalent, though, we're going to use this warm-up here, which is on two expressions. It says your teacher will assign you one of these expressions for when we did this in class, but what I'll have you go ahead and do is pause the video and evaluate these two expressions when n is 5 and when n is 7. When we say evaluate the expression, it means we're going to take that 5 and replace n with 5 in this expression, and also replace n with 5 in this expression and see what it ends up equaling. So we'll get to do some math. As you're doing your math, you might remember what we had done back in, if you took pre-algebra with us, or just from past math classes. We've got PEMDAS, or some people use BUDMAS to help them with these problems. So that's just my friendly reminder. Go ahead, pause this video now and evaluate those two expressions with those numbers. All right. Hopefully you paused the video and you tried to evaluate these expressions, starting with 5 for both of these. If I wanted to evaluate this expression when n is 5, it just looks like us swapping out the n with 5 and then doing some math. We could say 5 squared gives us that 25. That means on top of our fraction in our numerator, we have 25 minus 9. That is equal to 16. Down here on the bottom of our fraction in the denominator, I see 4 minus 3. I can say that equals to 1. And then we've got 2 times 1, which equals 2. Finally, I'm left with 16 divided by 2, which gives me 8. For this other one here, if I were to substitute 5 for n and go through and replace all my n's with 5, we can do the math here. That 5 plus 3 gives us 8. Over here on our other part of our problem, we've got that 5 minus 3 gives us 2. Down here, some students sometimes start by doing that 8 minus 3, but if we're using order of operations, PEMDAS, I need to do this multiplication first and then the subtraction second. So I could multiply, and then 8 minus 6 gives me that 2. 2 divided by 2 gives me 1, and I've got 8 times 1, which gives our final answer of 8. Looking here, we've got 8 for the first one and 8 for the second one. If you do those same steps with 7, for this first one here, you would end up getting 40 over 2, which simplifies down to 20. And for this one here, you would also get 20. So pausing here and looking at our answers, you might notice they're the same. If you substitute 5 for this first expression, you get 8. 5 for the second expression, you get 8. 7 for the first one, you get 20. 7 for the second one, you get 20. And that's going to be true no matter what number we substitute. Remember, the theme of today is all about equivalent equations. These right here are an example of what something looks like when it's equivalent. The starting problem, that starting expression we had, they look really different, but we're noticing that when you go to solve each of these and simplify it down to a single number, we end up getting the same thing for both. That is the idea of something being equivalent. It might start off and look different, like these two problems here, but in the end, we get the same solution. The difference with what we're going to be focusing in today is these were expressions. Remember, expressions are not equations. Expressions look like math problems that don't have what it's equal to. That was what we were trying to figure out here. Today, we're going to be looking at equations and building on what we've been talking about in this unit so far. So to continue us on and do exactly that and explore this idea of equivalent equations, we are going to start here for this first activity, which we called Much Ado About Ages. Our goal for this activity is to write as many equations as possible that could represent the relationships described below in parts A and B. If you think back to some of the lessons we've done earlier in this unit, there's been some other situations we've looked at where we actually came up with more than one equation that could represent that situation. The idea here is similar. So looking at part A, we've got in family A, the youngest child is 7 years younger than the oldest, who is 18. Our goal as we were saying before, is to write as many equations as possible that could represent that situation there and the relationship between the two children in this family. If you're struggling to figure out where to start with your equation, think about if you need a variable in this situation. And if you do, like, what is that variable going to represent? AKA, what's the thing we don't know in this situation? And use that to help you get you started. I'm going to encourage you to pause this video, see if you can come up with at least one equation. If you want to challenge yourself, see if you can come up with a couple more, and then come back to the video to see if your equations look the same as mine. Alrighty. Hopefully you tried to come up with an equation for this one. For family A, we have the youngest child is 7 years younger than the oldest, who is 18. As I read through this, I notice I know how old the oldest child is. The oldest child's 18, but that youngest child, they don't tell me an actual age for that youngest child. So there is my variable. For this first family here, let's say Y represents the youngest child, specifically the age. Give me a second. This will make it easier. Y is the age of the youngest child. When we go to come up with our equations, remember we said there's multiple equations you can come up with. Some people see the word younger here and they think of subtraction. One of your equations might be, well, that oldest child is 18, and I would have to subtract 7 to find what? Well, to find the age of the youngest child. And there's our Y right there. You might have thought subtraction, but had something in a different order. You might have said, well, if that oldest child is 18, if I subtract the younger child, that gets me 7. The difference between that oldest child who's 18 and the youngest child, who we don't know how old they are, is 7 years. I'm using that word difference there because we've learned that can mean subtraction. Looking especially at this first equation here, you might have figured out we can actually solve and figure out how old that youngest child is. The youngest child is 11. That can be really helpful as you try to create more equations to make sure these equations are true. This here is showing me my youngest child is 11, so I could check this other equation I wrote by thinking, could Y be 11? We're still talking about the same family, so if this equation is telling me that youngest child is 11, this one should be as well. If I think through that, we've got 18 minus our youngest child, which we're saying is 11 years old. 18 minus 11 gives us that 7 there. Now, the way you can represent this situation doesn't just involve subtraction. You could also come up with an equation with addition too. I'm going to give you 2 equations to look at. See if you can figure out which one is the one that could also represent this situation. One of the equations I'll give you is Y plus 18 equals 7. I said 7 and I wrote Y. And then our other equation, I'm going to give you Y plus 7 equals 18. Take a moment, think about those 2 equations, see if you can figure out which is the correct equation to represent this situation. The other way you can think about this is by saying our youngest child, if we were to add 7 years to them, that's going to get you to the oldest child. And by saying it that way, that helps us figure out it's this equation here. That youngest child plus 7 years gets you the age of the oldest child. This one right here wouldn't make sense. If I solved this equation, we would see that youngest child has to be a negative age. We know from earlier that youngest child is 11, and look at this last equation here. If I picture Y equals 11, we get 11 plus 7 equals 18. So this one here is another equation that represents the situation. Now remember, the theme of this lesson is all about equivalent equations. These are 3 equations that look different, but they all represent the same situation, and more importantly, they all have the same solution. All 3 of these equations, if we were to solve them, we would get that youngest child is 11 years old. So they're all representing this situation and describing that same solution of that youngest child being 11. Now we've got one more family here. We've got in family B, the middle child is 5 years older than the youngest child. Again, pause that video and see if you can come up with at least one equation. If you want to challenge yourself, try to come up with a couple more and then come back to the video and check to see how you did. And go. All right. So similar to how we started that first one, I think a good starting place is to figure out what are our variable or variables. What are the things we don't know in the situation? And family B, the situation's a little different than family A because here I don't know the age of either of these people. I don't know the age of my middle child, so maybe I'll say M represents the age of the middle child. I also don't know the age of the youngest child, so I could say Y represents the age of the youngest child. Quick reminder, remember the letters you choose for your variables don't matter. Make sure you know what that variable represents. Don't just throw in letters and not know what they mean in the situation. So you could have used like X here, X and Y instead of M and Y, as long as X also represents the age of the middle child. We've got our two variables. That's going to help me get to my equations here. This time we are talking about a middle child being 5 years older than the youngest child. So maybe your equation started off with addition. We could say whatever our youngest child is, we need to add 5 years to them to equal that middle child. Now with these equations that have more than one variable, sometimes it's hard to know if the equation you've written is correct. Above, we were able to actually find the solution for that situation. We were able to figure out that that youngest child was 11 years old. Down here, we have two variables. Do you think I can come up with a solution for this situation? I can come up with possible solutions, but there's no one correct answer for this. They didn't give me enough information. But we can use those possible solutions we can come up with to help us figure out if our equations are correct. What I mean by that, I'm going to make a quick table over here. I'm going to say Y represents the age of our youngest child, M is the age of the middle child, and just make up some possible correct solutions for this situation. For example, I'm going to pick a random number. We're going to make that youngest child 10 years old. If our youngest child is 10, do you know how old the middle child would be? Well, if the youngest child is 10, the middle child is 5 years older, so the middle child would be 15. We can pick another number. Maybe that youngest child is 20. How old is the middle child? Well, they're 5 years older, so they would be 25. You could also do it in a different order. You could make up a middle child age. I'm going to pick 20. If my middle child is 20, how old is my youngest child? Well, we're working backwards now. So if my middle child is 20, my youngest child should be younger. It should be a smaller number. Instead of adding 5 to get the middle child, I'm going to have to subtract 5 to get the youngest child, and we get 15. And let me clean up my table a little bit. This isn't necessary for this problem, but it can help you confirm that your equation you came up with is correct. For example, if I pick any pair of numbers in my table, like that 10 and 15, I could check this equation I just wrote by substituting 10 for Y and 15 for M and saying, yes, that's good. It satisfies my equation. It gives me a true equation, a true statement. So it helps me know that this equation correctly represents the situation. Now, just like the others, there is more than one possible equation. Did you guys come up with anything else? Well, thinking about how we were getting these different values in our table, we said one way is you can add 5 to the younger child to get the middle child. That's what this equation is describing here. Think about what we did for this last pair, though. I gave you the middle child, and to get the youngest child, we had to take the middle child and subtract 5 to get the youngest child. There's another subtraction equation you could write too. Instead of this one, do you know what that other subtraction equation could look like? We'll notice for each of our pairs here, the difference in those ages is 5. I could write an equation for that by saying our middle child minus our younger child. So the difference between those two children is equal to what? Well, it's equal to 5. For all of these equations we've written, I could pick any pair of numbers in this table of like possible ages of the kids, put it into my equations, and see that it gives me a true equation. If I write an equation that doesn't correctly represent the situation, like my youngest child plus my middle child equals 5, if I were to substitute a pair of numbers for the possible ages, so for example, we said it's possible that the youngest child's 10, the middle child's 15. If I try putting that into my equation, Notice I'm not getting something that's true. That's a sign to me that this equation doesn't correctly represent the situation. I'm sure there is a family where their younger child plus the middle child equals 5. Maybe like the younger child's 2, the middle child's 3. And so their ages together equal 5, but not this family. So that equation doesn't represent our situation here. Now we've got 3 equations here. How could I describe these 3 equations? Remember, the theme of this lesson is equivalent equations. All 3 of these equations here look different, but they represent the same situation, and they're all describing the same solutions. Here, I don't know exactly what that solution is. I don't know the age of those 2 kids, but all of these are correctly describing that. And if I did know the solution, so let's say those 2 kids are 20 and 25, each one of those equations, if I put 20 and 25 into those equations, would show me a equation that's true, a statement that's true. We are going to continue this idea of exploring equivalent equations and shift from us writing different equivalent equations to thinking of like what things mathematically can you do to an equation to get another equivalent equation. And to help make that description there make more sense, we'll come down to this next part, which is called what's acceptable. So that's what I mean by thinking about like what math can you do to an equation to get another equation that is equivalent. In this section here, we've got Noah is buying a pair of jeans and using a coupon for 10% off. The total price is $56.70, which includes $2.70 in sales tax. Noah's purchase can be modeled by the equation, and then we've got x minus 0.1x plus 270 equals 5670. I'm just going to pause us here before we even worry about the questions. Looking at this equation that was given to us, it was given to us, but it's important we still understand where it's coming from. I encourage you to pause the video and think about what each part of this equation means. So that x, what does x represent here? The minus 0.1x, what part of the situation does that refer to? The 270, the 5670. Pause the video and see if you can label each part of that equation. That'll be a good check to see if you understand where this equation is coming from. So go ahead and pause the video now. All right. Coming back, we had said we were going to look at these different parts of the equation and see if we can figure out what each part's representing. When I did this in class, everyone started with that 5670. What is that 5670? It's tempting to say it's like the price or the total. I want us to be as specific as possible here. That 5670 is the total price. It's the total price after the coupon. So after Noah uses that coupon and the sales tax is added in. So that is like the official price you are paying for those jeans. I think most of us know when you go into a store and you see a price, it's not actually the price you pay because stuff happens like sales tax. And so that 5670 is that final price. Well, that final price is coming from 3 different things. That 270, they told us right here, that's our tax. So the 270 that we're adding in, that's that sales tax being added in. Now we've got these first 2 parts here, which is where our variable is. In order for us to make sense of this equation, we have to know what that variable x represents. It comes back to the very first part of the story. It was saying he was buying a pair of jeans. That x right there is the price of the jeans. It's not the total, like final price after the coupon and the sales tax. We could maybe describe it as like the original price of the jeans before the coupons added in and before the sales tax is added in. So that x right there, that's our original price of jeans. That minus 0.1x then is that 10% off coupon. If you change 10% into a decimal, it looks like 0.10 or just 0.1. So we're multiplying that by x. We're finding 10% of our original price of jeans. So I'll come in real quick and label that is that coupon or that money we're saving from the coupon that we're taking off the original price of the jeans. Hopefully that helps us answer these first 2 questions here. I will be your partner that you're discussing with. This first part here says, what does the solution to the equation mean in this situation? And then that second question we're thinking through is, how can you verify that 70 is not a solution, but 60 is the solution? Go ahead, take a moment, pause the video, think through those questions, give yourself a chance to think through them before you come back in and we can discuss together. When it comes to this first part, what does it mean to be the solution to this situation here? A lot of people sometimes think that 5670 is the solution. Our solution isn't that total price at the end. Your solution is the same thing you'd be solving for if I asked you to solve this equation. It's that X there. And we had already said what X represents. It represents the original price of the jeans. So if you solved this equation and you found, for example, 100 is the solution, you figured out that original price of jeans. So here, our solution represents the original price of the jeans. Figure out what the solution is, we're talking about X. So for the second part then, knowing that our solution is talking about X and that original price of jeans, how could you verify that 70 is not the solution? Well, if 70 is not the solution, it means that 70 is not the original price of jeans. I could verify that or prove that 70 isn't the solution by putting 70 into this equation for X. I could say 70 minus 0.1 times 70 plus 270 equals 5670. You do that math, it looks something like this. Yep, I typed that right. And then 70 minus 7 gives you 63. And 63 plus 270 does not equal 5670. If 70 was the solution, remember, I should be getting an equation that's true, but 63 plus 270 is 6570, not 5670. So that's how I can show that 70 is not actually the solution. The second part of that question says, but 60 is the solution. So they're telling me 60 is the solution. How could you check to see that 60 is the solution? Well, by doing the same thing. Let's put 60 in for X. The math would look something like this. And when I do that math on the left side, what am I expecting to see? Well, I'm expecting to see that it does in fact equal 5670. We get 60 minus 6 plus 270. 60 minus 6 is 54, and 54 plus 270 does in fact equal 5670. That's how I can confirm that 60 is in fact the solution. If it's the solution, I should be able to put it into my equation and get something that's true. Before we move on, we keep saying 60 is the solution. What does that mean in this situation? Well, if 60 is the solution, and the solution represents the original price of jeans, that means that X, that original price of jeans, is $60. It means Noah bought a pair of $60 jeans, and when he used that coupon for 10% off, and he paid his sales tax, he ended up paying $56.70 for that $60 pair of jeans. It's important to understand this equation and what that solution means, especially when we're talking about equivalent equations, which is the direction we're headed in now. What we are going to do for the rest of this section of the notes is look at other equations that relate to this original equation here and talk through three things. So for each equation that I give you, these are the three things we're going to talk through. We're going to figure out mathematically what was done to get that equation. Remember, this is the equation we're starting with, this one right here. So we're going to talk about mathematically what was done to that equation to get from this to the new equation. We're going to interpret what it means in this situation. So when you do that math, what does it mean about the story we're talking about here with Noah and the jeans? And then we're going to ask ourselves, would that new equation have the same solution? To get us started, I'm actually going to have us start with equation B. I hope that's okay. Looking at equation B, it is the equation X minus 0.1x equals 54. Just to help us out, this was this equation, the original equation that we've been looking at. 5670. So comparing that original equation with this new equation here, I've already done the first part for us, which is mathematically what was done. Well, to get from this equation to this equation, I notice that 270 is gone. What I did to get that new equation is I subtracted 270 on the left side, and I also subtracted 270 on the right side. Now the interpretation is, what am I figuring out when I do that? So we can think of it kind of as like, what does that 54 represent? If I take away that 270 and I get 54, what does that mean in this story about Noah and the pants? Well, that 270 was that sales tax. 5670 was the total for the jeans, including the sales tax. But when I take away the 270 on both sides, I'm figuring out the total price before sales tax. Or you could say like the price of the jeans, including the coupon, because that coupon's still there, but without the sales tax. Now, when we're thinking about these two equations, and if they would have the same solution, I think thinking about this math that was done can be really helpful. At this point, you guys know how to solve equations. That's something we did in pre-algebra. So think about when you've learned how to solve equations, is this legal? Are you allowed to subtract the same number on both sides of the equation? The answer is yes. When we talked about solving equations, that was like a huge thing. Whatever you do on one side of the equation, you got to do on the other side of the equation. So I like to call this, I wish there was a better like mathematical sounding way, but I like to say this is legal. We're able to subtract 270 on both sides of the equations. That means that this new equation here represents the same story. The X here still is describing a $60 pair of jeans. It's just showing me the price before sales tax instead of the price after sales tax. But we're going to say for the same solution, yes. If you don't believe me, how could we check to see that it's the same solution? Well, we know from earlier the solution is 60, so I could check it and verify by replacing x with 60, just like we did before. And we get 60 minus 6 does in fact equal 54. So this second equation right here has the same solution as the first equation. Because they have the same solutions, we can also say that they are equivalent equations. One way you can find an equivalent equation is by doing that same math on both sides, like subtracting 270 on both sides. Now coming back to this first one here, we skipped this other equation I wanted to look at, the 100x minus 10x plus 270 equals 5,670. Here's our original equation. I'm gonna just copy that up there for us. And comparing these two here, I want us to think through what math was done. How did I get from that equation in the red to the second equation below it? See if you can figure out what math was done. You might have been able to figure it out. If not, looking at this interpretation might help you figure it out. The interpretation of this second equation here is that the price is expressed in cents instead of dollars. So we are saying, instead of saying you could pay a total, when all is said and done, of $56.70, we could say you are paying a total of 5,670 cents, or like 5,670 pennies. So what math was done to get there? Well, this equation was changed from dollars into cents using multiplication. How many cents is in $1? 100. We multiplied this first equation here by 100. And I want to be more specific. What did we multiply by 100? Did I multiply x by 100? Yep. Did I multiply that 0.01x by 100? Yep. 0.1 times 100 gets you to 10. Did I multiply this by 100? Yes. Did I multiply this by 100? Yes. So we could say we multiplied everything by 100. Or you might say we multiplied both sides of the equation by 100. That was mathematically what was done to that equation. Now, kind of like we said before, is that legal to do? Can you multiply both sides of an equation by 100? Yes. When we talk about solving equations, that's exactly what we do, right? Whatever you do on one side, you do on the other. So when we think about this last question here, same solution, is the solution for this first equation and the solution for the second equation the same? Are they both describing that same pair of $60 jeans? The answer here is yes again. We could say that's $60 pair of jeans you were paying 5,670 cents for, or you can say you're paying $56.70. You can say you're paying $2.70 in sales tax, or you can say you're paying $270, or you could say 270 cents in sales tax. They're both talking about the same amount of money and the same pair of jean price. So here we've got the same solution, which means that they are also equivalent equations again. We've got two other ones that we're going to do like this. Coming down here to number 3, this time we are looking at this equation here. Once again, I will put that original equation we had here at the top. This time I'm going to have you pause the video and see if you can do all 3 parts here. The first part's already done for you, so make sure you read it through, and then see if you can come up with these other 2. Go ahead and do that now. Alrighty. So for this first part here, I gave you the answer. To get that second equation, I subtracted 270 from the left side, and I added it to the right side. Now let's think about that. That's taking away the sales tax on the left side. We saw earlier, if you take away the sales tax, then that amount you're paying before sales tax should go down, not up. So if we're interpreting this here, I could say maybe like I removed the sales tax and the price before sales tax went up. When you think about, would these 2 equations have the same solution? Are they both describing $60 pair of jeans? You might have actually gone in and done the math and substituted it in for 60. If you do that for this new equation, 60 minus 0.1 times 60, which equals 60 minus 6, does not equal 54.70. $59.40. So when it comes to do they have the same solution, our answer here is no, they don't. To kind of help explain why they don't have the solution, think about the math that was done on this equation. We said on one side of the equation, we subtracted a number. On the other side of the equation, we added a number. Is that legal to do when you're talking about working with equations? And the answer is no. I have so many students who tell me they've heard this probably from so many math teachers. Whatever you do on one side, you have to do on the other. And that wasn't done here. On one side, we subtracted. The other side, we added. So because you're doing something that's not legal, we're getting a different equation. That's not to say this equation doesn't represent a pair of jeans. You solve this, you're going to get a different cost for these jeans. So these jeans could exist out there. They're just not talking about the same situation anymore. They're not talking about our $60 pair of jeans anymore. So when we get to this last part, they do not have the same solution because we know the solution for that first equation, 60, but the solution here isn't 60. And because they don't have the same solution anymore, they are not equivalent equations. Both of those equations aren't representing our same situation about Noah and his $60 jeans. There's one last one for us to look at, equation D. I'm going to have you go ahead, pause the video, and try this one now. For this last one here, when you go to look at what math was done, we multiplied one side of the equation by 2. So we could say we multiplied, I'll say the left side of the equation by 2. Everything on that left side was multiplied by 2. That 56.70 there stayed the same. And we talk about why you would want to multiply something by 2. You're multiplying by 2 because maybe Noah bought 2 pairs of jeans. So we are multiplying there the price for 2 pairs of, the price for 2 pairs of jeans, the discount you would get on 2 pairs of jeans, and the sales tax you would get on 2 pairs of jeans. All of that would be doubled if you bought 2 pairs. But this final part here, that final price he's paying is still $56.70. When we think about that, does that line up with our other situation? Is this describing the same pair of $60 jeans? The answer is no. If you're buying 2 pairs of jeans and we're doubling everything on that left side, the price you're paying should go up. The price you pay should double. If you get double the amount of genes or twice as many genes, you should be paying twice as much. So here, this doesn't match up with our situation. This is describing a cheaper pair of jeans. This is describing a pair of jeans that when you get two of them, you pay $56.70. We saw earlier when he was getting one pair of jeans, he paid $56.70. So again, we're not describing the same pair of jeans. So when it comes to that question about do they have the same solution, our answer is no. X here doesn't equal 60 anymore. It's going to equal a cheaper cost of jeans. There is a way you could multiply by 2 and get an equivalent equation that has the same solution. Any ideas what it is? Well, if I did want to get two pairs of jeans and I wanted to keep these equations equivalent, you can't just multiply one side of your equation. You also have to multiply the other side. Something like this would still have the same solution as the first one because we're doubling the price of the jeans he bought, we're doubling the discount, we're doubling the sales tax, and we are doubling that final amount of money he would have to pay. They would have the same solution, and they would be equivalent equations there. The last part of this lesson is really focusing in on things like this. What mathematical move or what mathematical thing can you do to one equation to get a new equivalent equation? And that is what this last part down here is going to look like. For example, I'm going to give you two equations like this, and our goal is to figure out would they have the same solution. Now, I do want to recognize we could sit here and solve all of the equations on the screen and compare the answers you get when you solve them and see if they're the same solution or not, but that's not what the focus is here. There's a way to identify if they have the same solution without actually having to solve any of these equations. And it's related to what we've been doing here. I want to compare the math I have to do to get from one equation to the other. So for example, with the situation here, I want to think about what math do I have to do to get from 3x minus 5 equals 16 to 3x equals 21. I'm trying to have them line up a little bit over there. Thinking about what math you can do to get from one equation to the other, we're going to ask ourselves, is that a good thing? Is that a legal thing that we can do? If our answer is yes, then it means those two equations are going to have the same solution without us actually having to finish and solve them. So for example, looking over here at my two equations, can you figure out what math I did in this empty space right here to get from that top equation to that bottom equation? Take a moment and see if you can figure it out now. Well, as I'm looking at them, I notice that minus 5 disappeared. How did I get it to disappear? Well, I came in and I added 5. On the other side, I notice I went from a 16 to a 21. I also added 5 over there. Looking at that math, I ended up adding 5 on both sides of my equation to get from that top equation to the bottom equation. That's legal. We can do that. We can add the same number on both sides. So when it comes to the question of do these have the same solution? Let me put it down here. Do they have the same solution? My answer is yes. There's another part to this question, and that is, are they equivalent equations? What do you think? Are those two equations equivalent equations? Well, the answer there is also yes. If they have the same solution, it means they're equivalent equations. Remember our definition of equivalent equations. They look different, but they describe the same solution. It turns out that both of these equations here are describing the solution x equals 7. You don't have to solve that to figure it out because we can focus in on this math we did here. I'm going to give you a moment, see if you can figure out for these 5 here, are they going to have the same solution? And are those equations equivalent equations? Pause the video now, take a couple minutes, and see if you can figure them out. All right. For this first pair here, what was done to get from that first equation to that second equation is they distributed. They distributed that 4 to the x and the 4 to the 2. So they just simplified the left side there. Are we allowed to simplify? The answer is yes. Simplifying something is a legal move that you can do. So when it comes to, are those going to have the same solution? They do have the same solution. When it comes to the question, are they equivalent equations? They've got the same solution. So they are indeed equivalent equations. This next one here could be a little tricky for some students to figure out what math was done. Remember, there's only 4 types of math. So you could check and see, like, can I add something to get to one to the other? Can I subtract something? Can I multiply something? Can I divide by something? Using that and just eliminating the ones that don't work, you might be able to figure out to get from a 6 to a 2 and a 12 to a 4 and a 9 to a 3, we were dividing. I was taking 6x plus 12 equals 3, and I divided everything by 3. For some students, dividing everything by 3 looks like this. For other students, they've also seen it as I'm dividing both sides by 3. So you can show I'm dividing everything on that side by 3 and show it like that with that division line going all the way across. And I'm also dividing everything on this side by 3. Again, that question, is this a legal move? Can we do that? Yes, we can. Dividing the same number on both sides of the equation is an okay thing to do. So similar to simplifying, this is allowed. We can divide both sides, and when you do so, that new equation is still going to have the same solution, and that new equation is going to be equivalent to the old equation. If you solve this equation and you solve this equation, both of those equations are going to have the same number for x. That number, by the way, ends up being negative 0.5. Coming to these next two here, I think both of them are very similar. For both of these sets here, that plus 1 kind of just seems like it came out of nowhere. If I was starting with my 5x equals 10, in order to get that second equation, I had to add 1 on one side, but not on the other, to get 5x plus 1 equals 10. Same over here, I added 1 on one side of the equation, but not the other. Are we allowed to do that? Well, we keep saying whatever you do on one side, you got to do on the other. I can't add 1 only on one side of my equation. I'd have to do it on both. So when we think about, is that a legal thing to do? Just adding a number on one side and not doing it on the other? The answer is no, we can't do that. The reason we can't do that is because it would not have the same solution. These two equations here aren't describing the same x. Those two x's have different values, different answers. Because they don't have the same solution, that also tells us that they are not equivalent equations. This part right here is true for both of these problems here. This last one, I'm going to have to move my face. We've got our 2x plus 3 equals 5 and 4x plus 6 equals 5. Can you figure out what math I did to get from that top one to the bottom one? Well, here, if I'm starting with a 2x plus 3 equals 5, to get the 4x and the 6, that's what changed in the second equation, I would have to multiply 2x by 2 and multiply 3 by 2. My 5 stayed the same, so I wasn't multiplying over there. So in order to get 4x plus 6 equals 5, I multiplied one side, that left side, by 2 to get 4x plus 6, and then did nothing on the other side and kept that 5 there. Again, the question, is that allowed? Do they have the same solution? Are they equivalent equations? The answer to all 3 of those questions is always going to be the same. No, that is not allowed. If you multiply on one side, you got to multiply on the other. So no, they don't have the same solution, and no, they are not equivalent equations. I'm going to summarize that by just putting a big no there. Now, there is a way for you to multiply by 2 and get an equivalent equation. If I want to multiply by 2 on that left side, I also have to multiply by 2 on the right side. So I could say 2x plus 3 equals 5 is equivalent to the equation 4x plus 6 equals, I got to multiply the 5 as well. 5 times 2 gives me 10. Now that set there, that is a pair of equivalent equations. If you solve both of those equations, they'd have the same solution for x. X would be 1 for both of them. And because they have the same solution, they are equivalent equations. Feel like you've probably never heard the word equivalent so much. This lesson can be a little more challenging for students, so feel free to reach out if you've got any questions. If not, thanks so much for watching. Good luck on the homework. Have a good rest of your day, and see y'all. Bye.